Hello, I'm Mr. Lineweber, and this is lesson 6.4, the Law of Conservation of Energy for Science 10. So today we're going to focus on the first law of thermodynamics that we brought up in the last video, namely that energy cannot be created or destroyed. It can only be transformed from one form to another. And we learned in the last video that for every one of those transfers, there's always going to be some sort of waste energy, and there is no such thing as a perfect or ideal machine. However, when we are working in problems that involve the law of conservation of energy in physics, what we often do is we treat the system as isolated, which we learned in the last video that it's an ideal case, in which the total amount of energy within that system never changes. And in other words, what we're talking about basically is that in most questions we will be ignoring friction. So the reason we ignore friction is because friction is an external force that would act on the system that would remove energy from the system to the surroundings in the form of heat. Thus, in the absence of external forces, kinetic energy may be converted to potential energy and vice versa without any loss. So the total amount of mechanical energy remains constant. So again, this is an ideal case because we learned in the last video that no energy transfer is perfect, but in some of these math questions that we're going to do, we will assume that it is a perfect transfer of energy. So I like this symbol here to show the transfer from potential to kinetic. And we have an example of a pendulum here. And so when the pendulum is at rest, it would just hang here in equilibrium. Somebody outside of the system has to set the pendulum into motion. So someone has to come in here and do work on the system and bring the pendulum to its maximum height. Then once the pendulum is at its maximum height, it can be dropped and set into motion. And what that means is it's just going to follow your intuition. It's going to just drop and fall back and forth, and there are forces involved. So there's the force of gravity that's always acting down on the object no matter where it is. And then we have the force of tension through the thread of the string, through the bonds of the particles that are connecting the fiber, whatever it is, a chain or a cable or string. Okay, and those forces, we're going to consider them internal to the system itself, such that any of those forces doing work are just going to transfer one form of energy to another without any loss. So we're going to get potential converted to kinetic, and we're going to get kinetic converted to potential. And so like I was saying before, someone has to do work, lift this pendulum, and now at this state of the pendulum, what it has is this high potential to fall. So what we have is an EP max, and that's gravitational potential energy is a maximum at this location. And then as it's dropped and the pendulum swings into motion, at this lowest point, all of that potential energy gets converted into kinetic energy. And so we have a maximum kinetic energy at the lowest point because all of the potential energy has been converted into kinetic. And then what happens as it swings across to the other side, then its maximum kinetic energy, as it swings up doing work against gravity, then that's maximum speed and that maximum kinetic energy is sort of lost to the gain in the potential in the fact that you're going up against the force of gravity. And then you're at a maximum potential energy, and then it swings back and then back and forth and back and forth. One way to think about this is a bar graph. And so the total mechanical energy of the system never changes because we treat it as isolated. So for example, say you had 10 joules of total mechanical energy. This bar on the bar graph will never change. However, these two bar graphs, what they can do is they can change going up and down, and whatever loss in potential will be a corresponding gain in kinetic and vice versa. So the way that it's drawn now, where it has more kinetic than potential, but it does have both, it means that you're in some in-between spot. And because it has more kinetic than potential, maybe I'll sketch it closer to the bottom here, since it has more kinetic. Now, let's pretend that the pendulum is swinging up towards its maximum. Then that means that it would be slowing down to a stop up at the highest point. And so what would happen is this bar here would go down as this bar goes up. So maybe at this current stage, maybe there's 6 joules of kinetic and 4 joules of potential. And as we swing upwards, then the potential energy is going to grow. And so what's going to happen is this bar is going to grow, and so maybe it's larger, and then this bar here is going to shrink, and then maybe it's smaller. So no longer is it the 4 and 6. Maybe now it's like 8 and 2 as the pendulum gets closer and closer to its maximum height. So to reiterate, the total mechanical energy remains constant, but the potential and the kinetic, those bars can change in terms of growing and or in terms of gaining and losing energy. So typical questions for energy conservation involve an object that is dropped, or in the question below, someone jumps up into the air and we want to know how high they get into the air. Alright, so for when an object is dropped, it has this potential to fall due to the force of gravity. And when it's at its highest point, we call that the EP max. And so all of the mechanical energy is stored in that potential energy term. If it's dropped, its initial velocity is 0. So it has no kinetic energy to begin with, and its total mechanical energy is potential only. When the object is about to hit the ground, the moment before it hits, it'll have a maximum EK, or maximum kinetic energy. And so what's happening is all of this potential energy is being converted into kinetic energy because the force of gravity is doing work on the object. So to use conservation of energy, we say that mechanical energy initial equals mechanical energy final. And so at the beginning, you have potential energy, and at the end, you have kinetic energy. And so mgh is going to equal 1/2 mv squared. On both sides of the equation, you can see the term m, so we can cancel that by dividing by m on both sides. And since we're asked to calculate the speed, we have to isolate for this value v. So to isolate that term, we're going to use inverse operations. So the opposite of 1/2 is 2, so I'll times by 2 on both sides. So I have 2gh equals v squared. And then to get rid of the square, I can square root both sides. And I'll get the speed is the square root of 2gh. So 2 times 9.81 times 12 square rooted 15.3 meters per second. And that's the speed of the object the moment it hits the ground. The moment right before it hits. Now sort of the opposite version of this is when you're on the level ground and you jump up into the air, and so you start with a whole bunch of EK, so you have an EK max, and you have no potential energy to begin with since you're starting on the ground. And so the force of gravity is going to do work against, or you're going to jump, and the force of gravity is going to do work on you, slowing you down. And so if you're slowing down, where does your kinetic energy go? Well, it's being converted into potential energy. And so to use the conservation of energy, we say that the total mechanical energy initially equals the total mechanical energy final. That's energy conservation. Energy cannot be created nor destroyed, only transferred. And in this ideal situation, it's a perfect transfer. So we say that 1/2 mv squared equals mgh. And so it's pretty much the exact same start as the last example, except on this one I started on the left-hand side with mgh because that was my initial. And here I'm starting with 1/2 mv squared because that's my initial. Divide by m on both sides. And in this case, we're trying to find the vertical height that the child reaches. So I got to solve for h. So that means I just have to divide by g as well. And so I'll have 1/2 v squared divided by g, and that will give me h. So 0.5 times 1.6 squared divided by 9.81. And I get 0.13 meters. So it looks like the child was able to jump 13 centimeters into the air, so not very fast. Or not very high. Alright, this next question, it really will summarize all the major components of this topic and this concept. And so it is sort of the premium example for the law of conservation of energy. So you have this system of mass. So here's your object that is 90 kilograms. And at the science 10 level, it's usually started from rest. So you can see here, started from rest. Now in physics 20, that object can be coming in with some initial velocity at the beginning, and so they don't always have to start from rest, but in science 10, usually it does. And so the total mechanical energy at that location, it is potential only. And so that's going to be your EP max. And that EP max is your total energy. And that total energy is going to stay the same if you're going to use the law of conservation of energy. And if you're going to use the law of conservation of energy, you have to assume that you are in an isolated system. And to assume you're in an isolated system means that you're going to have to ignore friction, as friction is an external force that does work in order to remove energy to surroundings as heat. So, analyzing this question, this is going to take the natural path that you would assume it would, and this mass system is at the bottom of the hill, as it's used up all of its potential to fall, it's now going to have an EK max at the bottom here. And as the mass system continues up in this frictionless system, you would expect that you would slow down going up this hill. And so because you've only gone halfway up the hill, you're not back up at the top at the 10 meters, you're only 5 meters up. At this location, you actually have both potential and kinetic because you're in some in-between place. Just like in the pendulum, you have EP and EK at any location in between the maxes. But at this equilibrium position, it would be EK only. So that would be gone, and you would be, this would just be the entire 10 joules. It would just be EK only if it was at this equilibrium position. But if we swing it up to the top, then this is only going to be in EP, so all of it gets transferred over. EK completely gets depleted, and then your potential only when you're at this maximum height. And so the same thing is happening here. At this location, you have a full energy bar in potential. That bar goes to 0 as the EK bar goes up to its maximum height, and it'll be the same height on that bar graph as this one when it's at the bottom of the hill here. But at this location, you're going to have 2 bars that are going to contribute to the total. So there's both potential and kinetic. And then what happens is that this mass system ends up smashing into this tree. And so the question is, how much work is done on that tree? Well, the work done on that tree is actually going to be the change in kinetic energy of the mass system, which is basically its final speed minus its initial speed. And its final speed is going to be 0 minus its initial speed. So the work is going to get transferred. It's going to be all of the kinetic energy that was in the system is going to get transferred to the tree. Okay, so we just have to calculate their speed. We've done these things. Okay, so let's take a look. So at the top of that hill, you have EP only, and at the bottom of the hill, you have EK only. So this is that first law of thermodynamics, the law of conservation of energy, where all of the potential gets converted into kinetic. You can divide both sides by mass. We're going to solve for speed. So 2gh square root equals v. And this is a pretty common isolation of variables, so you should get used to it. 2 times 9.81 times the height. You can see that it doesn't even depend on the mass. The mass gets cancelled out. So 14 meters per second will be the speed at this location. So the V max is 14 meters per second. Okay, so I think they want us to show the potential energy total. So mgh, so that's going to be 90 times 9.81 times 10. That's 8829 joules. And the EK max should be the same value using 14, so 0.5 times 90 times 14 squared. And I got 8820 because I rounded. And so you can see here that it's nearly perfect energy transfer, and I just rounded in my value, and that's why it didn't work out perfectly, but it is the same. It is the same because that's what we said it was going to be right at the beginning. Okay, and so that's what they're trying to get us to show here. Okay, so the more important part is what happens when we get up here. And so we have the fact that ET is going to remain constant the whole time. So ETI equals ETF, and so they're just using T for total mechanical energy. I was using M earlier for the same thing. Okay, so I can use either one of these locations. It doesn't matter because it's the same value and they're both a max. So I'll just use the MGH, and that was the initial height that we dropped from. Now the total energy final at this new location, it has both EP and EK, so that's going to be MGH final plus 1/2 MV squared final. Now I can divide both sides of the equations by M, so I can get rid of M everywhere. Divide left and right by M. So I got 9.81 times 10. I got 9.81 times 5 plus 1/2 V final squared. So this is 98.1. This is 49.05. Subtract this to the other side. So minus 49 minus 49. Alright, so we got 49.05 equals 1/2 VF squared times both sides by 2, and then square root. And so we have 9.9 meters per second V final at that location. Okay, so this mass total, if it was going 14 meters per second at the bottom of the hill, it's now going 9.9 meters per second at this point here. And then it's about to collide with this tree. So how much work is done on the tree? Well, it's the total change in kinetic energy to bring the toboggan, the mass total, to a rest position. So it's going to be EK final minus EK initial. And so the EK final is 0 because it comes to rest, minus the kinetic energy that it went in with. So it's going to be minus 1/2 M, and I can use this 9.9 that I just found squared, and that's how much energy is transferred to the tree. So I can square that 9.9, times it by the math, and then divide by 2, and it looks like 4.4 times 10 to the 3 joules, so that's kilojoules, and that's how much work is done on the tree. Alright, so the rest of this lesson is just sort of some theory and some quick discussions to have. So we're looking at evidence of energy conversions, and so often in our word problems we're looking for changes in motion or changes in the vertical position, and so that's the changes in gravitational potential energy. So just to reiterate, because it's such an important concept, we have a high potential energy location here because of the potential to fall due to the force of gravity. And then here we would have a high kinetic energy position because of the transfer of potential to kinetic. So, evidence of energy conversions. Change in shape. So, elastic potential energy, it's discussed in Physics 20, and sometimes you get some questions in your word problems about work done pulling a string, for example, in a bow and arrow. So often they would give you the average force and the total distance displaced so that you can calculate the work. And remember that the work done is the area under the force position curve. And often this force is not constant, it's changing, and it actually requires some pretty advanced math to solve for this. Changes in temperature. That means that thermal energy is being converted or transferred. Thermal energy is just heat. Change in chemistry, so if particles are actually changing the way they're organized, so for example, this is the combustion of methane into carbon dioxide and water vapor, and energy is released. So this is just a combustion reaction of a fossil fuel. Those are studied in the chemistry unit. And from the biosphere, we have photosynthesis and cellular respiration as sort of inverse processes of each other. You can see here for photosynthesis, energy is required, and we have this output, making the sugar. And cellular respiration, the sugar is the food, so to speak, and in the presence of oxygen, we're combusting and energy is released. And so that's from the bio unit. And fossil fuels are formed from dead organisms compressed over time. Combustion reactions convert chemical energy into fossil fuels into thermal energy. Yeah, that's what we showed here. So some technology that is always shown in Science 10, the hydroelectric dam, the coal burning power station, and the solar cells and the nuclear. So we'll get to all four of those briefly. So in all energy conversions with technology, there's got to be some transfers, typically to electrical energy at the end, and then we can use that electrical energy to power our devices and power our homes and heat our homes and all these things. So hydroelectric. So if you had a dam where you were able to pool water, lots and lots of water, so then it has to be at a position of high gravitational potential, so you can use that potential for that water to fall. That falling energy is converted into kinetic. That kinetic energy turns these turbines, and on those turbines, what you have is it's a system that's set up where you have a whole bunch of magnets rotating around on that turbine around coils and coils of wire, and what's happening is a changing magnetic field, which is those magnets rotating around in a circle. That changing magnetic field can actually induce current in the coil, the copper coil typically, and the electrical energy is produced, and that's taken to the power line, which is sent to the grid, and then we use it. And coal burning power station, or in fact any type of fossil fuel burning power station, we know coal, we're trying to reduce how many coal burning power plants we have, as they are a large fossil fuel emitter. But for example, in Alberta, natural gas is a big one. And so in any of these types of plants, what's happening is you have the chemical potential energy of the fossil fuel being burnt, and you get thermal energy of boiling water. So you can see that here in the combustion chamber. So steam is created. That pressurized steam is going to drive the kinetic energy in those turbine blades, and it's the same story as the last example. The turbine blades are connected to the generator. The generator has the magnets on it. Those magnets are going to rotate around coils of wire, and electricity will be produced, sent to the grid. Solar is a little bit different. So solar energy conversions and solar technology takes incoming particles of light, so those are called photons, and those photons are able to interact with specific particles, and you can see here they have a silicon layer with boron and a silicon layer with phosphorus, and that's just some technology that's been developed. They know that light, certain types of light have enough energy that those photons can interact with the electrons in those materials, and the electrons are actually sort of like kicked out of their atoms because of the incoming energy from the photon. And it looks like these two layers are going to set up what's called a potential difference. And so what that means is you have a whole bunch of negative charge that builds up on one plate and a whole bunch of positive charge that builds up on another plate, and this is due to this electron transfer. And so you end up with what's called a potential difference, and it's like it has the potential to fall, like gravitational potential. Well, these electrons now have the potential to move around a circuit, and so you can power some sort of device like a light bulb. Nuclear energy conversions, the one that's demonstrated in this diagram is called fission. This is what is done in power plants on Earth. So we have a uranium atom here, and you can see that it's the way that it's drawn. The fact that there's not these like little diagrams around it means that it's stable. So this is the natural state for this uranium isotope. And then the technology is that we bombard the uranium with a high energy neutron, and so that neutron is actually able to embed itself into this uranium, changing the isotope, and then this new isotope of uranium is not stable, and what ends up happening is there is this internal impulse that splits the atom into two, and what ends up happening is energy is released because of what's called a mass difference, which was predicted by Einstein. Okay, and so we have in Canada some nuclear power plants in Ontario, and you can see here that they're using uranium. It undergoes nuclear fission, releasing nuclear energy. Well, this radiation, they have safety measures that protects people from that, so there's nothing to worry about there. And following the energy conversions, that's what we're interested in. It's the same idea as all those other ones. It's just how do you get the heat? The initial heat comes from the nuclear reaction, and it's a chain reaction. It's like millions and millions and millions of these atoms are undergoing this, releasing energy. It's like a chain reaction, exponential, releasing energy, and it's just, you know how powerful it can be. And it's the same idea. You're going to get some turbines spinning, turns the generator, electrons are moved into the system or the grid, and then we can use that electrical energy. Solar energy, and this bullet right here, solar radiation, is the radiant energy emitted from the fusion reactions within the sun. So fusion, that bullet there, it really is why we're all here. Without the sun, obviously, there would be no energy to sustain life. So the sun is the source of energy for pretty much everything on Earth. And fusion is a little bit different, because if you compare it to what we just talked about, fission, you saw that this uranium sort of broke into two smaller atoms. So it's like a big atom breaking into a smaller atom. Well, fusion is a little bit, well, it's basically the opposite. So you're going to have smaller atoms, like two hydrogens. They're going to be under enormous pressure and heat inside the sun, and they're going to form a larger atom like helium. So two hydrogens are going to form a helium, and energy is released. And it's also a chain reaction, and there's millions and millions of these reactions taking place every second, and so you have massive amounts of energy being released as it's like nuclear bombs going off on the sun all day, never ending, pretty much for our lifetime. So all of the next bullets are the result of solar energy, so or indirect solar energy, indirect. So wind and water cycles, due to the uneven heating of the Earth's surface and the surface of the ocean, you're going to have places of places that are warm and places that are cold. And convection currents, for example, you're going to have warm air rising or warm water rising, and cold air or cold water falling as it's more dense, and you get this cycle of some up, some down, and then this creates motion, and then this is wind and water. And we can use wind and water motion in the hydrologic cycle and the wind to help us produce energy. For example, solar farms, or pardon me, wind farms, like turbines, wind turbines. Hydrologic cycle and falling water we talked about. Biomass is any organic matter that can be combusted to release chemical potential energy. And so we're talking like, for example, wood from trees or any organic waste from landfills or garbage. And basically fossil fuels are the biggest indirect biomass that we use, and so fossil fuels are formed from dead plants and animals over hundreds and millions of years of biomass under extreme heat and pressure. And you can see my cool little diagram here. You can see that we have to drill quite deep to get at these oil and gas deposits, and you see that we are dependent on these in our current society. And this is the biggest question for climate change, and is our fossil fuel dependence. We are 100% dependent on it. If we were just to rely on wind and water, it wouldn't work out right now, especially in Alberta. So maybe nuclear energy is the answer. If it's done right, this could be our answer to climate change, but the economy and the politics will determine that. As we move forward, geothermal energy, this is energy from the core of the earth. Still not, you can't use this wide throughout the entire country. It's just too hard. It's too much demand and not enough supply. Tidal energy, same thing, energy from the tides. Like maybe if you're in a specific location, you could get it to work, but it's probably not enough to supply everybody's needs. And the difference between renewable and non-renewable. So renewable energy sources are continually and indefinitely available, like solar, wind, and water. Non-renewable energies, limited and irreplaceable, like fossil fuels and nuclear. Energy demand, there are several factors that have caused increased demand for energy. That's obviously population, and as more and more countries become industrialized, more people around the world are going to use the Earth's resources. The effects of energy use. The extraction and combustion of fossil fuels can negatively affect ecosystems. And so oil spills from tankers of cars trying to get across the country. There's lots of online videos about ecosystems, especially from the oil sands, that are causing disruptions to basically any ecosystem. Release of greenhouse gases, this is huge because of climate change and rising CO2 levels and global average temperature increases, and melting ice caps, and then other issues like acid rain. And the one thing I'll say about this is this will be the biggest, one of the biggest debates in politics and economics. And it is the hardest thing to negotiate. It's like how much of the environment are we willing to sacrifice so that we can have a strong economy? And it's always difficult with different parties in power and how the politics can play a huge role here. Energy consumption and conservation. As energy use continues to rise, fossil fuels will be depleted. Not too sure about this. They always give like warnings like 50 years, 60 years, but there's a lot of fossil fuels in the earth, so I guess we'll see. Alternative energy sources must be developed. Expensive, difficult to incorporate. Basically, like, businesses want to invest in things that they know are going to work, and so this is a big topic in today's society is, are we willing to fund and invest in alternative energy sources to get away from fossil fuels? And until feasible alternative energy sources are developed, one of the best ways to try to improve our practices is through conservation and improved efficiency. One way to do that is cogeneration, is using the waste from one process to power another process. But the biggest one here is anything that is considered sustainable development, which has like net zero emissions, which means they'll absorb as much carbon as they emit. And so sustainable development is economic development that meets the needs of current generations without compromising the needs of future generations. And this really is the key for us moving forward as a society.